G'day people. Had a few requests on these GPX units. Well, this is the GPX 5000 and very similar to the GPX 4500, except it's got that extra timing, that fine gold timing in the 5000. And the other thing it's got too, if you want to have a look here, it's got, well, I better zoom in on that as you won't be able to see the ants. Okay. You've got your plus and minus 5 volt power supply here, the feeders, well, inductors, 2 capacitors, another inductor. And you also here on this, on the 5000, you have a BC857 and a 8.4 volt Zener, or some people call them Xena the Warrior Princess diode. And also on this unit as well, there is a bank of capacitors here, which 2 are for the rail that supplies this op amp here, and 2 go somewhere else. I've actually never worried about those. I better have a look. But the critical ones are the outputs here and here, and these are supplied by the FMM or whatever, FMTT 618 and 617 under the board. It's really amazing when you have a look at you know, what these devices have to handle, trying to make smooth voltage rails and working with very sensitive receive equipment like op amps in this configuration. You know, you think they've used very low on resistance components, and yeah, the power supply is a bit rubbery, if you ask me. Yeah, no dry throat today. I've got some fizzy water. So what I'm going to do, I'm going to fire this gadget up, and I'm going to do the positive rail first, which is this one here, closest to me, and then we're going to look at that negative rail furthest away. So -5, +5. I've got the oscilloscope in AC coupling. There's a reason for AC coupling, and I'm going to show you, because what we're going to be doing is looking at the ripple on those 2 points, and I've got the oscilloscope set for 5 millivolts per division, and the time scale is 200 microseconds. So what we'll do, we'll turn it on, and this will be quite interesting. This is not the detector I was working on yesterday or the day before. This is a different one. So at the moment, if I just put the oscilloscope lead near it, it's going to pick up the transmit pulses all over the shop because it's floating. Okay, so what we'll do, we'll say, okay, we want to have a look at I want to have a look at something. Hang on a second. It just went nuts. I don't know why I did that. Oh, hang on a sec, I know why. I was cleaning the board with a bit of methylated spirits, and I left it there. Hang on, I'll just shoot that with some, I'll just hit that with some contact cleaner. That'll get rid of that metho. Metho has water in it. I use it because it's cheap. And I've got bottles of it where IPA, for a can like that, something like 30 bucks. So I'll just blast it around the op amps there, and that'll displace the water. Not that it'll hurt, because it's only a little bit of water in the methylated spirits. And I'll just get a cotton bud, give it a bit of a scrape around there, so we don't have any water. It still might go off with contact cleaner, but it should be less. We'll just see what happens. So she started up. Yeah, it's got a little bit there in here. Look, I'll just blow on it. You listen what happens. It'll behave. It'll behave in a minute. I'll just use a dry cotton bud now, just to get the rest of that off. Touchy things, aren't they? Anyway, apart from all that rattle and noise and so forth, I'm going to connect the oscilloscope earth lead to the middle of the board. On the test point that I do, you can see that jumping up and down. Now, what we'll do, we'll go onto the positive supply of the op amps, which is there. Okay, you can probably see that quite easy. You can see the switch mode power supply on times. Then the line goes straight. That's the switch mode turning off. The switch mode runs at the same time as the TX waveform or T transmit output. And what happens is that when it turns off, it relies on what's basically stored in a few capacitors. And yeah, well, if you have a look at that, that DC line there is not very good, is it? We have probably, I can lift it up, but I'm guessing about 3 millivolts of ripple on the positive line. There shouldn't be any there whatsoever, but it is there. It's on every detector, by the way. Every detector has that. Basically, there's trade-offs in getting that correct, and I'll explain that in a minute. Okay, now have a look at the negative rail, right? This one here is a bit of a dog's breakfast. There's your negative rail. Look at that. That's not very good, is it? We have in excess of 5 millivolts variation in the supply. And yeah, for some reason, that negative rail, even in the transmit side of things, it's dipping. That's telling me that the capacitors are not large enough on the, probably all the capacitors in these detectors are probably not large enough to do what you want. That's woeful. That's really bad. But anyway, this is some of the reasons these detectors can be noisy, because the supply rails are a bit shoddy. That's just me slipping off. Now, the other ones we got here, we got the supply rails to this other op amp. Now, we remember it's one is, we'll get onto these ones here. Okay. I think that's negative actually. I'm going to be careful doing this. I don't want to slip with the oscilloscope probe because it's very, very close to everything. That's just me pushing on the board, putting my fingers on the coil. Okay, that's obviously ground. It's very, very straight. You can just see little remnants of the switching power supply for the transmitter there turning on and off. But I'll go to the other side of this. This is interesting. Actually, I don't need the noise. We'll turn the noise off and just look at the things. Okay, I don't know if you can see that. That is the supply on the positive side of that op amp. Look at it. Hang on, it's probably just needs a level tweak. But I don't know if you can see it very clearly. I'll just zoom in a bit more. I don't know if the timing of the camera and the... Oh, hang on, I'll just loosen that off so I can move it easy. Somewhere around there. But have a look at all that fast ripple where it's meant to be nice and clean. I would say that would be having a performance impact. So that's one side of it. And if I get on the other side, I think that was the positive supply. I'll get on to the negative. Oh God. Did you see that? I don't know if you saw that. If I get on it, there we go. There's your DC negative supply line, right? What the hell is going on there, right? Now, I've always just taken it for granted with these detectors that things like supply lines would be fairly clean. That is, no, I'm not joking, that is the negative supply line to the op amp, which controls, as far as I know it does, in my opinion, is part of the SCTA airfield cancellation network. Well, so that's a bit of an eye-opener, isn't it? Now, you think to yourself, well, we can go and stick some small inductors in there and capacitors and all sorts. Now, this is where it gets tricky. You can't just do that. Now, I'll zoom out again, right? I'll show you on another board. I'll stick this down here, but I'll poke another. Where's my crappy board, which someone tried to strip and wrecked it? It's over here somewhere, I think. Here it is. I use it to catch hot melt glue now out of the hot melt glue gun. But if you have a look, I don't know if they're still there. They've probably been taken off. Oh, yeah, anyway. Oh, damn. It's under the hot melt glue that I stuck on there. Anyway, get that off. Okay, we'll get a pointy implement. You can see that this has been, over the years, it's been raided for some parts here and there. Oh, to the fellows in the US who are asking me as well, they got audio problems with a GPX. These resistors and capacitors here, it's an audio network, coupling and decoupling and so forth. If you got audio problems, the audio just disappears or makes squeaky sounds and misbehaves, I've found that some of the surface mount resistors here can go open circuit or they can go high. But I've found, many times I've found the problem for the audio in this area here. Okay, and a very easy way to tell, this will sound completely unscientific. Turn the detector on upside down. Make sure first that you've scraped away some of the white paint from the ends of the surface mount components so you can get some contact with them. Lick your finger and touch it. And if there's any audio problems in this area, you'll get audio out of the detector into the speaker or headphones or whatever you're using. And then take your finger off, it'll go away. It'll slowly fade off as the moisture dissipates off the surface mount resistors. So yeah, if you ever lose audio, lick your finger and touch just there, right? Make sure you don't do it around here. 200 volts, zap, zap, you're gonna fly off the back of the chair, right? Don't touch anywhere around here. You know, we've got a 40106 that sits here. I think it's a 40106 for memory. That's floating. That's got 200 volts on it. You touch that, you get belted. You touch the capacitor, which that you get belted. You touch here, you can get belted. That's where, see, I was saying the other day about they only use one diode here as provision for two, because you don't need the second because it's connected through on the other diodes. But anyway, all the GPs had the diode here, and then they realised they didn't need it, so they took it out. So yeah, that's the audio. Sorry for getting off the path there, but I do remember someone emailed me. I looked at it this morning and I said, I'll just get that in there. Okay, what we have our little, where are they? I'm trying to find where they are. Okay. Why does this board look different? Can't be different. It's got to be the same. No, that's right. Okay. Here, these are your power supplies. We'll call this the capacitance multiplier circuit, because if you see the waveform from the rough power supply that goes into these, you'll just go, what the hell? It looks like the Himalayas, right? It's a mountain range that looks like it's going in. It's really bad, but anyway, it's into these capacitors here, and it acts as like a capacitance multiplier, and fairly clean, within reason, fairly clean DC comes out. Now, if I remember rightly, these are the ones that blow up if you short out your op amps or anything happens to the op amps. There's a what is it? FMMT? It's FMMT 718 lives there. These are devices, you get these through, they were ZX or ZTEX, however you say it, but now they call themselves diodes. What a mundane name, but diodes is the name of the company. And that's the 718 there. That, for memory, might be the positive one. Whatever blows up, I'll replace it with whatever it is. I don't go run around trying to see if it was a positive or negative in most cases. And the one up here that was there, that is the FMMT 618. So if you ever lose your 5-volt rail on the op amps, either a positive or negative, it'll be one of these. These things, they're good. I think the 718's good for about 1.5 amps. The other one might be good for 2.5 amps. Sounds like a lot, doesn't it? 1.5 amps out of a little tiny surface mount device, little SOT23. Yeah, but the problem is when these are supplying the voltage and whatever current they can put out, and they go, see, this is the other thing I was going to point out. This is a 4500 board, right? Okay. You see here, it had the extra capacitors here, and the two devices here, the 8.4 volt Zener and the BC 857 was here. And we don't have any extra components or supply for that part of the SCTA circuit, right? That's a big difference between the 5000 and the 45, but I still think the 45 overall, the early ones like this is, you can tell it's an early one because it's got the pins there and there. That's a big giveaway that it's an early one. And anyway, what do you say here? You go, oh, okay. Now what you've got here in the middle, and making sure I'm just in frame, you've got a capacitor and a capacitor. Then you have an inductor and an inductor. So negative comes in here, goes through this inductor, and the inductor at the end of this inductor is connected to that capacitor. So they're joined like so, and that runs off as a negative rail to power the op amps. And the other things, BF 998s and all sorts of things down there do have power going there. I just can't remember, it's 5 or 15, but anyway. Whatever it is. But you say to yourself, okay, well, we've got a problem with this ripple and noise. Let's start adding extra capacitance, right? And the thing is, or you can say, oh, we'll just increase the inductor values. And I'll tell you, do not do it. Do not do it. Because if you don't do it right, this is what happens. You turn the detector on, it basically turns on those FMMT 718 and 618, and it looks at those extra capacitors as a very, well, usually you'll have a fair bit of capacitance there to get rid of that amount of ripple, and it'll make a very, very low impedance, or basically a very low ESR if you want to be technical about it. So depending on the ESR of the capacitor or capacitors, these things will try and drive that low impedance instantaneously, and they can't do it. They do not like heavy impulse current trying to supply it, and you'll have smoke pour out from the bottom of the board. It'll take one or both out, okay? This is a common occurrence. So when you have to, or when you want to try and clean up the supply rails for that part of the circuit board around here, there's not much room to put capacitors unless you want to put them here. You've got to keep your lead short, else they're going to be ineffective for a start, because you're looking at fairly high switching rates and ripple. And you know, if you can get this ferrite sleeve, maybe you can jam it in there rather than here. That's just a real estate hog. You don't want to put componentry over the input stage here. You may get interactions with current pulsing in and out of inductors, capacitors, and it can influence the very low level input stage. You get the slightest movement there of, you know, basically the capacitor having current pumped in and out, and it will generate a very slight electromagnetic field as it does that, and it can interact. The other bugbear I think too is these capacitors here for the transmitter, very, very close to the op amps here. That possibly may cause some interaction with the power supply starting up and shutting down, starting up very, very fast. I think it does it around 28 kilohertz or something from memory, and possibly, I'm not saying for sure, my opinion that this could act on the noise floor of this part of the circuit. This should be, yeah, what, in the middle of the circuit board over there, away from anything. Go stick it near the microprocessor or something, you know. Yeah. But it's just a layout of the board. I mean, you've got to have your transmitter, and I suppose it's logical to have your receiver as close as you can to the you know, coil connector, and try and keep things away. But you know, it is difficult. Maybe if they change the configuration of these the transformer or the inductor, I don't know. Maybe there's enough room there. This is only an inductor, by the way. You could have piggybacked it up the top on here, and because they're like a semi pot core type thing, they're like an expanded E core. You know, they're pretty well shielded, but they shouldn't interact. But you know, just the configuration of how things are in the new detectors, I've noticed that configuration is a lot better throughout the boards. You know, they've got all the digital stuff up one end, sitting there chugging away, and all the low noise receive stuff up the other end. It's really good. Yeah, so this is an issue. We got these crappy looking supply rails, and they all do it. It's on all these detectors. So you got the supply rail on this one and that one going to these op amps, and they're the little capacitors here. I think you can probably see those. I'll zoom in just show. These are your capacitors. Oops. Oh, that's stiff. That's, I think that one does a positive rail, that does a negative rail, that does positive rail, and there's meant to be one for the negative rail on that one, but I've never found it. I don't think it exists. You know, so yeah, maybe that's half the problem. I don't know, but you know, usually it's you know, plus, minus, plus, nothing. So I don't know where that is. I've looked, you know, I thought it might have been, you know, this one here or that one there. It's not. So maybe it's under the board, and I'm not going to go and scrape paint and poke around all the capacitors to find out. Maybe it is. I don't know. The other thing too, remember I was saying about that the other 5000. This is just for you guys who repair these things. It's not really for anyone else. Don't fiddle with your detectors. If you don't know what you're doing, you'll blow it up and you'll have tears come out your eyeballs. This one here, this is the 5 volt. Hang on, helps if it's in screen. Yeah, we'll move it around a bit. Here we go. This is the 5 volt MOSFET, power output MOSFET for the 5 volt pulse. Now, the one that was in here and that's been discontinued of all things had a metallization pad underneath the device. And I can show you what I mean by that, because I've got some blown up op amps that, yeah, where is it? It's there somewhere. I'll move down. Yep, go on. Where are you? I've got this thing zoomed in too far. Hang on. I can't move my hand in the right spot. Oh, I was looking at my wrist. Okay, if you can see this looks like a MOSFET. It's actually an op amp, but same thing, same package. You know, 4 legs that side, 4 legs that side. 1 leg will be the gate, 3 will be the drain, 4 will be the source, or the other way around, whatever it is, right? And normally you just say, okay, that's drain and that's our source, and fine. But on the ones they were using, these legs here, they're not connected. They're just stuck in the plastic of the device. There's no connection whatsoever. And you have to do a hot air treatment or infrared to be able to melt this down onto the board. It's got a pad where it can melt down onto the board. So because we can't get the ones with the connected pad because they were discontinued, you can put an FND 70 or 72, whichever one it is, whichever one does the most current. You want probably about instantaneous current rating, or you know, something can do peak current of maybe 20 amps, but a continuous rating of 3 to 5 amps or something like that. But anyway, if you have a look on here, I'm going to zoom in again. Otherwise, I only tell half the story. Okay, you can see on this that I've replaced this one. I've replaced that as well. And because I didn't have the original component, what I've done is I've soldered for the Americans, all those, still got this on, I can hear it. So there's me touching it. I've soldered all those legs together there, right? Because this one has the legs connected, but it has no underneath connection pad. And right next to it, can you see the solder? I've got it blobbed around. It just blobs around here, and I can show you on this board, I think, how they use the same parts. Yes, they have. Okay, making sure I don't want to show people the wrong thing. Okay, I'll rest that there. You can see here on this one, that's that part there where it was, right? And that's that pad, right? And these legs, they go nowhere. Those ones there, they go nowhere. They're fresh air. That's when I was poking it. You can have a look here. They go nowhere in the device. They don't go anywhere. They don't even connect onto the pad. But this pad connects right. If you can see, there's a couple of little holes. That's a through plate on a power pad from this. So that goes there. And what I've done on the new device, I've just blobbed all these with solder, and just built it up and cleaned off the paint, of course, and stuck it there. So we've got output from the device into the circuit. So if you can't get the original, whatever it was, I don't know what it was. I mean, I could go look it up, but not off the top of my head. You can just use another device and just, you know, connect its legs to that bit there. I'll just scrape this anyway. I'll scrape it and I'll show you what's there, just so you know. This paint on this one's an absolute pearler, I tell you. Some of the paint comes off easy, some of it doesn't. But this board's never going to work again, so I don't care. Now, if you have a look on there, I've scraped it. You can see where I've got the screwdriver there and given it a scrape. You can see that is just 4 through plates. That's connected to this, and then you can just connect on the new device, just blob all these legs together and just stick it on there, and away it'll go. It works beautifully. Acts as a big heatsink as well, so I've never had any troubles by doing that, so it's a bit of a thing. Now, the other thing too, from the guys in the US, I was saying about the audio problem. These guys work on these detectors, so they should know the rest of the circuit. I hope you do. I hope a particular company gives you a lot of support material so you can work on these. What else? I'm just trying to think of the audio problems. I mean, same thing with this. You know, you get that. Remember this one here, which you can't see because I'm not looking at my camera. There it is there. Remember this one here, if it goes short, the detector will just turn off. Or if it does come on, you'll have no detection depth whatsoever. It'll just clamps everything down, everything falls over, and it'll seem like it's on. Just depends how things fail to what you get. But anyway, that's always a culprit. Those things under the board are culprits. The front end transistors, you know, the front end MOSFETs, should I say, are one of the biggest culprits ever. And oh, they're still on this one. Ooh. Okay, I'm trying to work down. It's very hard. These things here, right? If you see where they are, where I am on the board, that and that blow up quite often. They're 200 volt rated MOSFETs. The thing about these, you want as low on resistance as you can get when they're turned on, but you want the lowest capacitance as well. You want extremely low gate capacitance, or else the drain source couples into the gate and the signal disappears. It actually impacts on the signal level getting into the first amplifier stage. You know, it's got to go past another couple of MOSFETs, of course. But, you know, these have got, well, probably, I think just around about 2 ohms each. And they're driven by this little, there it is there, see it, the screwdriver, that little device there, that's, it's actually not driven by that. That's actually a fast turn off the way it's set up. Anyway, there's a BAV99 there, and that gets driven through a 100 ohm resistor here, and that gets driven out of the ADG333, which is this gadget. And if you want to start looking at where the pins go off that, good luck to you. But when you replace these, if they do blow up, right, it can also blow up the other little ones on the other side of the board, which are in series with these going to the input to the op amps, the input op amps. When these go short, it can take this here out. Oops, there we are. Make sure I'm on it. It can blow that one up. And the other thing is too, if you touch a soldering iron and any of the capacitors on the 15 volt rail are charged, which is here, that's the two, sorry, here we go. That's one leg of the 15 volt capacitor, 15 volt filter capacitor, or reservoir capacitor in this case. And that one there's the other one. Short those out, because if you don't short them out, it'll discharge through here and blow that up. And it's very common. People have fixed these, put new parts in, and they turn it on, it goes bang, bang. And oh, what happened? Well, first of all, it took that out. that little little BC 857. It's a P channel, just bipolar, and nothing special about it. 20 volt rated sort of thing. And they're the 2SK1334s, which have been discontinued. You can still get them if you're very, very lucky. There are other devices you can stick in there. Philips have a device that does a job, but the specs aren't as good. It will work, except, you know, I was very lucky. I got 2 reels of 1,000 of these at one stage of those devices. So, yeah. And then I came up with that method of using the self-switching devices, BSP 139s, I think they were. You can do that. The intrinsic on resistance isn't as good as a hard switched device. You have to run them back to back to get the isolation. Basically, one isolates, turning the other one, make sure it's off, and the other one holds the other one off as well. Anyway, yeah, it does work. It works okay. It works okay. It probably work really good for, you know, look, if you're looking for, you know, big gold deep. When you crank the speed up, the clocking speed of these, the self-switching doesn't work as well as it should. It's a little bit laggy, and you'll start, you know, getting signals in where these things should be off in the dead time. They're on, and you'll get leakage, and you'll get a noisy detector. So that's that part of it. But yeah, so at the moment we've got noisy supply lines, and I haven't checked the other 2 here to see how noisy they are. And I think I might just do that because they are there. I think they all might be, actually, we'll just see. I think they might all be connected together. And what I'll do, I'll zoom this out again so see what's going on within reason. There we go. What I'll do, now, you got to remember, 99.9% of repair work is done with a $10 multimeter, right? So don't forget that. You get your $10 beep range multimeter. That's your workhorse. Right? Actually, it really is. I do just about, I can run through this with a multimeter. I can find the fault, you know, relatively quickly, unless someone butchered those damn socket lines down there, which was the other video. That was a nightmare. That was really, really bad. I wish I had a whole board stripped down. You know, never had a part on it. That might have been a lot easier to find, but because everything's buried and iggly-piggly round and round, it was very difficult to find. So, yeah. So what I'll do, I just want to find out on these ones here if they're all connected together. Make sure I got my meter in beep range. Okay, nothing. And there. Okay. So the two on this end, which I've never ever bothered sussing, are connected together, and I would say by all chances they are connected to ground. All right. So the ground point, I've got it here, that we can use this ground point here. So what we'll do, yep, ground. So it's not a supply or a split supply rail pair of capacitors, it's for one supply. Both are grounded at the same end. I would say these are for, now I'll just check the other end of it, see if these are connected or not, are they? But we'll work it out. Let's have a look. We go there, and I'll go to this. That's just capacitors charging in it up and down. I bet you it goes to this device here, 857. If I get onto it, it's got white paint all over it again. Hang on. I'll make this a bit easier. I'll spread that out. But I know this regulates voltage to that, and so that's a Zener there, which is I'm pretty sure it's those two, is it? Oh yeah, no. I'll spin it around. Yep. So 0.74, that's a Zener there anyway. It's an 8.4 volt Zener. And I still want to find out where these are going. Okay. Okay. It's set up as a capacitance multiplier again. Okay. So this capacitor here, it's ground on this end. This is a positive end of it, and it is going to the base of that transistor. So it's set up as trying to regulate what's going into that transistor. Actually, I'll show you what's going into that transistor. You will say, how on earth can you get DC out of this, right? So that's just a little capacitance multiplier, and I'd say with the size of the capacitors they've got there, it's having a hard time doing it, but we'll have a look. Okay, I'll put a bit of audio on just so we hear it start up, make sure it's going to start up, make sure there's nothing around it's going to short it out. So she started up. Sounds better after that Mepho's dried out and gone away. But anyway, we don't need the audio. We'll just get the multimeter lead and we'll stick this. I'm just going to go onto the collector I'll go onto the base collector and emitter of that transistor, and we'll just see what lives there. But it is a voltage supply part of the detector, so we'll get there again. That's just resting on my leg, so you know that's me touching it. It's going all over the place. So I'll put it on a ground point in the middle of the board, and we will. There we are, we're picking up the transmitter, that's just leakage. Let's have a look on the collector. There you go. That's on the collector of that transistor, right? Isn't that just awesome? There's some DC. But yeah, look at that. Wow. But anyway, it's meant to be smoothed out, so that's going into that transistor. Let's have a look what comes out of it. Okay, we'll go on the emitter. And there's your output, yeah, DC-ish, right? With a good lot of ripple on the DC line. Now, I'll increase the bandwidth for this oscilloscope. So on 20 megs bandwidth, I'll just increase it to about 300 megahertz, whatever this thing does, I'm not sure, 400, 350, whatever. And we'll have a look at the waveforms there, and it's very furry with a lot of jitter on it. Wherever this is going into the circuit, it needs a little bit more capacitance on it. And I would say it looks like it needs capacitors set up for you know, very, very high frequency, low impedance, not too much capacitance, else, you know, things blow up. If these things turn on and try and drive something that looks like a short circuit to it for a couple of microseconds, it will blow up. So that's that. And what we'll do, we'll get on the base connection, we'll just have a look and see how filtered that is. And that's a lot of jitter there on the base. I think it's out of lock. Have a look. There we go. Well, you're going to get on the output what's on the base of that transistor, because the base is controlling what's acting as it's acting like an electronic capacitor, believe it or not. You sort of, if you give the base a very smooth signal, well, then it's going to want to hold the base at that smooth DC level, and the output should be the same. Well, within reason. There's going to be leakage and stuff, but that's not too bad after being fed a breakfast of wherever it is. There you are. Imagine getting that for breakfast and saying, make some DC out of that. Jesus Christ. Yeah. So yeah, anyway, if we go through onto pin 1, 2, 3, 4, pin 4 of that op amp, right? That's your positive. Look at that. That's your positive voltage going on to that SETA op amp. In my opinion, it's that. I don't know for sure. I didn't design the circuit, but you know, that's interesting. Now, I'll put in a disclaimer here. Maybe they designed it that way. Maybe it's part of the functionality of the circuit. In my opinion, I don't think so. But it may be, right? I'm just putting that there as a disclaimer. You work it out. And we'll go on the negative, wherever you are, somewhere there. There you go. It's flicking around like it's probably out of lock, but we'll just have a look. There, it's furry as well. It's furry. I can see very, very high frequency jitter on the DC lines there. But like I say, maybe it's supposed to be there. I don't know. So, there is some work that can be done on these detectors. Wherever it is, I'm zoomed in too far again. Oh, what would I do for a cameraman? But, you know, it works. But in my opinion, there is improvements that can be done. And the other thing too, when you start putting extra boards on the detector and you try and take it off these supply rails here as they are, you are going to make a mess, right? Because the more load you put here, the worse that noise becomes. The greater the jitter, the greater the voltage drops. It just goes completely bonkers. So, you know, I look, from doing power electronics years and years ago, I thought we used to have contactors used to switch, you know, 2, 3, 4, 500 amps, and just that switching used to blow the electronics up in the devices, you know, in the controllers. And we said, oh, you know, we'll go and get some bigger inductors, and we'll put bigger inductors in series, trying to limit the voltage rise. And all it did was make bigger lightning and blew it up twice as bad. So you can't go generally, you cannot just increase the inductance on these parts here and say she'll be right, because that means you're going to have to increase the capacitance, and you're going to run the risk of cold starting it and blowing the transistors up, right? So I've been thinking with the idea of, well, I've tried little commercial dual switch mode units, right? Generating plus or minus 15 volts actually, and I gave it away. They might as well put a bloody 100-watt HF transmitter in there. They are absolutely noise generators. You cannot shut them up. They just radiate. They're absolutely horrible. So, you know, you got to say, well, how are we going to get rid of the noise? It's damn difficult. Running a stop-start power supply system is inherently problematic in itself, and running it can, you know, running some inverter switch mode thing continuously is definitely going to put noise across the receive cycle timing. It just will. Trust me on that. You will not stop it, right? So what's the way around it? There is a way around it, but it gets very, very complicated. What you really need to do, and you could do it, is you get a decent sized battery pack, run a multi-leg cable into the detector, and give everything power off a linear supply for your transmitters, for your receivers, for everything. And depending how your batteries are configured, that would be the lowest noise way of doing it, as long as you decouple your leads coming into the detector. But a remote battery system that supplies, get rid of all the switch mode stuff, totally, just get rid of it, and have everything hard DC, decent sized capacitors there to hold it up, you know, a decent reservoir. And the improvement in performance, in my opinion, would be 2 or 3 times as good as what these are. It may even remove a lot of the EMI, which basically, a lot of the EMI is an intermod product with these things switching on and off. You have diode junctions in here which are going through a fully conductive to half conductive stages, then off, and all that non-linearity with noise coming in creates you know, a lot of odd order harmonics. It's possibly why these are so susceptible to EMI. You know, you can't go put filters on it because in all reality, the signals you're looking at are the same frequency as what the EMI is. And the time constants are all around the same area. You can't really filter that stuff out. You know, like doing it as a hard sort of brick wall type filter, you're just going to lose signal. You can't do it. You can put, if you did it digitally, you probably can put a couple of walls up and say everything in the middle and everything outside of that goes. But when you're talking input stages, you're trying to do something after the horse is bolted. You know, you're trying to modify something that's riding on other signals and that. And yeah, you can do a lot of oversampling and stuff like that and reconstruction. But, you know, you really want to come up with a way of just keeping these things clean. You know, if you really wanted a really good system, instead of running like a coaxial cable for the coil, you know, if you could run a balanced line, you know, if you could run a balanced line, which is, you know, a separate ground and the 2 coil connections coming back, and if you could, on the signal side, put it through a, you know, 1-to-1 transformer, there's going to be signal loss in that. So everything you do, you know, there's going to be signal loss. You could set these op amps up, you know, don't reference the non-inverting pin to ground, and make up a little subboard and see if you can run a balanced line system into these. And because you've got two op amps on there, if you want to run double D or cancel, well, you're going to use 2 double balanced lines. It gets complicated, doesn't it? Then you're going to have capacitance issues and stuff as well. You're probably going to, if you want to do it properly, you got to twist them together. You're going to slew rate limitations, extra capacitance. So yeah, it's a lot of thought, a lot of mucking around. Probably Minelab's probably thought all this stuff out over the years and tried it and said, oh God, you know, not doing that. It's too hard, doesn't work, whatever. Like I say, a lot of it's experimental. You can't go and buy a book on designing a metal detector and all the ins and outs on it. It's, you know, it's been basically black magic when it was first done with pulse induction. You know, I remember back in, what was it, 96, when the SD2000 came out, you know, it was just a wonderment. How does this work? And yeah, you know, people have, you know, tried to copy it and all the rest. I don't know if anyone's ever done a successful job of copying it, that it actually works properly. I think, you know, the first copies of the schematic, you know, someone sitting there nutting it out of a multimeter, got a few bits wrong, and it's been copied through to all the newer designs. And, you know, I've heard that they don't work properly. So, that's that. Anyway, how's that for a waffle? Let me have a look. Now, we're nearly on an hour on this. If you're still kicking around at this point of time, you're very, very interested in the technical aspects of metal detectors, or you're very easily entertained. One or the other, I don't know. But yeah, look, I've only touched on a very small part of this. Look how long it took to explain it all. You know, let's start examining the switching of all these 4053s here, or all these TLE 2027s here. You know, what they do, how they work, each channel. You know, we can have you can't look in these things. That's the trouble. You can't look in that, and you can't look in that. You can look at waveforms on the pins. You can look at the schematic of the device and get an idea of what's going on. But you won't know what's done inside it, you know, how it's programmed. That is a mystery. It'll probably remain a mystery forever. All in here is just power supply, supervisory circuitry. You know, it's even really funny when you think about it that you know, the master control oscillator for the transmit receive cycles, it's not digitally derived. It's actually an LC oscillator still. That's its inductor there. Capacitors somewhere under these devices on the other side of the board. That always strikes me as weird. You know, there's such a big distance between the inductor and the capacitor. Usually they're right next to each other. Anyway, it's not my design. I didn't design it. Someone else did, and that's how they did it. Anyway, look, you could talk about this thing for hours, and you know, I can go through I know what parts go faulty, and I know what it does, and I could probably explain all that out as well if you want to fix these things. But they are touchy, they are fiddly, and there's certain things you don't want to do because it will blow things up. And even worse than blowing up the components is blowing the tracks off the board, right? Or anything like that. If smoking the tracks, you definitely don't want to do stuff like that. These boards, you think, if you look at it, you go, oh, okay, it's, you know, tracks here, tracks on top, tracks on the bottom, right? Well, I don't think that's the case, because I've looked through here, and if you actually, I'll just move this up towards the light. If you actually get this, and where's the light? Oh, more. If you actually get this and hold it up to the light, well, the white paint won't block out white light, but you can see it's got an internal ground plane. It may have two internal ground planes. It may have only one, and it may be, you know, 8 layers of tracks in that board or something, especially around the microprocessor. You don't know. So that is something you can't look through, and you don't know. A lot of little tiny through plates are very, very, very tiny, and the only way you're going to examine those, because they're all covered with etch resist, which is on really, really hard and fast, is you need something like a pin on the end, like, you know, stick a pin on the end of your multimeter lead, or actually sewing needle. I've done that, and just poke into the padland of the resist near those through plates, and, you know, then you can say, okay, that's there, and then you can try and do it with another needle type thing and see where it goes. But the trouble is, you're going to have to probably look on the other side of the board in cases, and you're going to fall off, and it's going to move and slip and be all over the place, and, you know, it's a real nightmare. It really is. But yeah, so don't blow tracks off. Don't do what happened to me the other day on one of these detectors, where they busted the bloody data lines between going through the pads around. So in the around there somewhere, bloody round and round and round and back. Unbelievable. When that line was, I'm not joking, hair thickness. I don't know if you can see it on here. I had to scrape this back to see it. I don't know if we can get in. See those copper? I'll do it like that. That top copper one, right? It's thin as a human hair, that's broken over near pin 7 and 8 somewhere. It loops around there. I don't know if it actually is an internal track with a line, but it goes onto that resistor there, but it doesn't run the way you think it does. It goes in and around, and yeah, heavy fisted soldering broke those tracks. And you know, how would I ever know? You know, you just don't know. I had to nut it out, and it was very time consuming. Anyway, that's the 5000. Supply rails, I'll tell you this, the supply rails, which don't have these extra capacitors and things, on the on the 4500, the rails are a bit cleaner. Not much, they're pretty manky, but they are cleaner. And in my opinion, I don't know the reality of why this is between the early 4500. The early 4500, remember, has the pins, but some of them did change over to the socket with the mylar, with the black, you know, male holder on it, and then we went straight to these ones. So I'm just thinking, you know, what is the difference? The part of the gain is the difference, not the only difference. The other difference is these extra components, the extra power supply on the 5000, and on the on that 45. Now, if I put them side by side, you can just see it. I hope I'm not going on too much, but you know, if you see the 45's only got one bank of capacitors, and this one here has two, one there, one there. For me, because I've done a lot of work with big targets, and the 4500 on big targets, in my opinion, and you can witness it for all my other videos I've done when I've done tests side by side, the 4500 goes deeper on big gold. It just does. It is far more punchy. But then again, you know, the 5000's not a 4500. It's a different design. It's got different bits in it. Maybe it has different programming. It's got an extra mode. But, you know, like I said, did they crank the gain down to make fine gold work? It wouldn't work otherwise. I don't know. It's my opinion. So it was always marketed as a quieter, you know, detector, and I don't know if it was marketed saying it was a better small gold detector or anything like that, but I just find the 4500 is such a workhorse, fully adaptable, modifiable, run any damn coil on it you want. You don't have that dongle thing. You can get cheap coils for it. You don't have to go paying through the nose for your coils, like on some of the later detectors with their little handshaky dongle things in the detector coil or in the plug, depending on the model. These are relatively straightforward to fix. You can fix them in the bush if you really wanted to. You can see my other videos about fixing these in the bush. There's some common things that happen, and as long as you've got a hex driver and you know, a campfire, a bit of solder, and an old knife, and maybe you can fix half of it. You know, it might actually be advantageous to have a couple of those in a bit of silver paper wrapped up, and you know, a couple of input FETs, maybe the output FETs, the two little N channel FETs, they blow up too. What else? BF998 sometimes blow up, but BAV99s, just, you know, five components. You could probably fix 99% of the problems out in the bush on these. So yeah, I have got that turned off. Good. Yeah, that's it. That's an hour. Catches.